Good morning, everybody, and welcome to this second lecture. So, today we are going to talk about isolated singularities. Isolated singularities. So, what is an isolated singularity of a holomorphic function? So we have our holomorphic function f from u to c. U, as usual, is an open subset of C, for instance, this one. And then we have a point, let's call it z0, which does not belong to U. So z0 is not in U, but a whole punctured disk centered at z0 is contained in U. So there is here some small disk. So we have introduced this notation, dr z0 prime. So this is the punctured disk centered at z0 of radius r. So this means this is an open disk from which we have removed the center. Okay, and we are assuming that this set is contained in U. So this is a singularity, an isolated singularity of the function f. So here we are thinking about something like, for instance, functions like f of z 1 over z, then 0 would be an isolated singularity because the function is well defined, in this case actually for all complex number different from 0. Or functions like f of z equals sine over 1 over z. Again, this function is well defined for all z different from 0, and then 0 is an isolated singularity. Singularities which are not isolated are instead, for instance, if we look at the square root function. Now you've seen in the first part of this course that you can consider the complex square root as a function, as a holomorphic function, for instance, defined on the whole complex plane minus the negative half line. You have to take this half line away. So all the points here, for instance, the point 0, so these are singularities of this holomorphic function. Meaning that the holomorphic function is not as defined there, but they are not isolated. So there's not a whole punctured disk centered at 0, which is contained in the domain. Another example would be the logarithm function. That also has a singularity at 0, which is not isolated. Okay, so isolated singularities could, of course, be removable. What does it mean for a singularity to be removable? Let's give this definition. So the singularity z0 is removable if we can extend the function f, giving it a value also at z0 in such a way that it's a holomorphic function on the whole U union z0. So if f can be extended also to z0, so that it becomes so complex differential. at z naught, and hence holomorphic on U union z naught, which is still an open set because z0 was isolated. Okay, this is a removable singularity. And our first question today is when can we guarantee that a singularity is removable? And the answer is provided by the following theorem. So, the isolated singularity z naught is removable if and only if the limit for z going to z naught, c minus z naught times f of z is 0. Okay, so this condition is necessary and sufficient for the singularity z naught to be removable. Notice that this condition is saying nothing else but f of z is small o of 1 over z minus z naught for z going to z naught using the Landau notation small o. Okay, we want to prove this theorem. Of course, we need to erase the blackboard, so let's do it. Okay, proof. So maybe let's write here again the statement. Z naught is removable if and only if the limit of z going to z naught of z minus z naught times f of z is 0. So this is an if and only if, so we have to prove actually two statements. The first statement, so the first direction, this direction is of course trivial. So if z naught is a removable singularity, then so by definition f has a holomorphic extension at z naught. In particular, the extended function will be continuous at z naught. Holomorphic functions are continuous. And so if it's continuous, then this limit is 0 because f of z is converging to the value of this extended function at z naught times z minus z naught, everything is going to 0. So this implication is clear. What's relevant in this theorem is the other implication. So we assume this condition and we want to show that z naught is a removable singularity. In order to do this, we define a new function, g, defined on U union z naught, with values in C, by setting, so g of z is, so if z is in U, we define it to be z minus z naught squared times f of z. This for z in U. Instead, for z equals z naught, we define the function g to be 0. So z equals z naught. So now let's look at this function g. So this function is of course holomorphic on U, it coincides with this holomorphic function, and let's check that it's complex differentiable also at the point z naught. In other words, we have to look at the limit g of z minus g of z naught divided by z minus z naught. What is this? G of z has now this expression, minus g z naught, so minus 0, and then we divide by z minus z naught. What we obtain is exactly this quantity, z minus z naught, but to the power 1, we had a power 2, but we are dividing by z minus z naught, times f of z. And by assumption, this function is converging to 0 for z going to z naught. So this shows that the function g is differentiable at z naught and its derivative is 0. So g prime at z naught is 0. Okay, so g is now a holomorphic function on U union z naught. And as such, it has a power series expansion around z naught. We can write g as g of z equal sum n goes from 0 to infinity an z minus z naught to the power n. And this series will converge to g on some disk of radius r centered at z naught. Okay. Moreover, we know that the function g vanishes at z naught, and also the derivative of g vanishes at z naught. So this information tells us that the first two coefficients in the power series expansion of g are 0. So a0 and a1 are 0. So the power series expansion of the function g actually starts with n equals 2. Okay, and then we can write, so z minus z0 times square times f of z. So this is our function g for z different from z naught. So it has this power series expansion. So here I can write a sum, and here we found out that this is sum actually starts with n equal 2 to infinity an z minus z naught to the power n. And now if we divide, so this equality holds for all z in the punctured disk d prime r z naught. And if we divide both sides by z minus z naught, so this goes away, and here we get an exponent n minus 2. So we obtain that f of z is the sum of this series, an z minus z naught to the power n minus 2. And this is actually a genuine power series, because here the index starts with 2, so here we have only non-negative powers of z minus z naught. So f in this punctured disk is the sum of a power series, and as such it extends to a holomorphic function on the whole disk just by setting. The extension is obtained by setting f of z naught. We define it to be, so here we have to consider we have to look at the coefficient in this power series of the term with degree 0. So exactly A2. Okay, so if we define f at z0 to be A2, we obtain a function which is now defined on U union z0, which is holomorphic, because in this disk of radius r centered at z0, it coincides with the sum of this converging power series. Okay, so this proves this theorem on these removable singularities. And now, with this theorem, we can classify singularities of holomorphic functions. But before doing so, let me just write a remark concerning slight variations of the formulation of this theorem. So, what we saw is that, so the fact that the limit z minus z naught times f of z goes, so this is converging to z naught. The fact that this limit is 0, this is equivalent to the fact that z naught is a removable singularity. So f has a holomorphic extension at z naught. But of course, if f has a holomorphic extension at z naught, we can also say that f has a continuous extension at z naught, right? Because holomorphic functions are continuous. So if f has a holomorphic extension at z naught, in particular it has a continuous extension at z naught. And if f has a continuous extension at z naught, in particular f is bounded on some puncture disk around z naught, on d prime r z naught for some r positive. If the function f is continuous at the point z naught, then in particular it is bounded in a neighborhood of this point. And so we have this chain of implication, and this fact here, the fact that f is bounded on this punctured disk, implies also that this limit is 0, because we're multiplying a bounded function by something which is going to 0. The result is something which goes to 0. So we conclude that actually all these conditions are equivalent. So in particular, the singularity z naught is removable, for instance, if and only if f has a continuous extension at z naught, or if and only if f is bounded near z naught, or if you want, if and only if this condition holds. So what we proved in the theorem is so this is sort of the apparently weaker condition. It's implied by these other two conditions, but actually all these conditions for holomorphic functions turn out to be equivalent. We will use this fact all the time. Okay, now let's go to the classification of isolated singularities. So, isolated singularities can be of 3 different kinds. One kind is, we have already seen it, z0, z0, sorry, z naught could be an isolated, could be a removable singularity. And we've already seen the definition. F can be extended as a holomorphic function also at z naught. Let's see immediately an example. We could consider, for instance, the function f of z equals sine of z divided by z. So the natural domain of this function is c minus 0, because we are dividing by z, which vanishes exactly at 0. And this is, of course, a holomorphic function on this open set. And what is the limit for z going to 0 of sine z divided by z? This is a classical limit. I'm sure you know what this is. This converges to 1. So this function has a limit, meaning that f has a continuous extension at 0 by setting f of 0 equal 1. If we set f of 0 equal 1, we get a continuous extension of f. And by the theorem we proved before, this extension will actually be a holomorphic function. So 0 is a removable singularity. So this function can be extended to a function which is holomorphic on the whole C. And of course, in this particular case, we don't need to use the theorem we just proved. One could, for instance, use the power series expansion of sine and write 1 over z times the sum n goes from 0 to infinity minus 1 to the power n divided by 2n plus 1 factorial z to the power 2n plus 1. So this holds for all z in C minus the origin, the domain of our function f. And now we just observe that, so we are dividing by z, so we can remove this and just reduce this exponent by 1. And here now we see this is an honest converging power series, and so f is on the whole, so f is the sum of this converging power series, and therefore it defines, so this sum defines a holomorphic function on the whole C. So the singularity at 0 is removable. Okay, these are removable singularities. The second possibility for an isolated singularity is that an isolated singularity could be a pole. So z naught is said to be a pole if it is not removable but there exists a natural number k such that the function z minus z naught to the power k times f of z. So if we multiply our function f by z minus z naught to the power k, now the singularity at z naught becomes removable. So such that this function has a removable singularity. At z0. Okay? And in this case, if this is so, then the smallest value of k for which this is possible is called the order of the pole. The smallest natural number k with this property is called order of the pole. Z0. Okay, so this definition is of course modeled after rational functions. So here is our example 2. Let's consider a rational function. For instance, f of z equal z minus 2 divided by z minus 1 times z plus I to the power 3. Okay, so this is a rational function. It's the quotient between two polynomials. And so this rational function is defined on C minus, so the singularities are at the zeros of the denominator, namely at 1 and at minus I. And both, so both 1 and minus I are isolated singularities. And I claim that they are both poles. So, more precisely, 1 is a pole of order 1. Indeed, if we multiply f of z by z minus 1, then this cancels, and we find a function which actually has now at 1 a removable singularity. The function that we obtain by removing this is well defined, and so it's also holomorphic in a neighborhood of 1. Instead, the singularity at minus I, so minus I is a pole, but of order 3. Okay, so here we have to multiply this function f by z plus I to the power 3 if we want to remove the singularity. You can easily check it. If you multiply by a smaller power of z plus I, the resulting function will not have a removable singularity at minus I. Okay, this was an example of so two poles of a rational function, but also more general holomorphic functions may have poles. For instance, let's look at the tangent function. So this is our example 3. So f of z is the tangent of z. So this is sine of z divided by cosine of z. So this function is holomorphic on C minus, so the tangent is not defined exactly at the zeros of the cosine function. And the cosine functions are the complex numbers of the form pi half plus k pi for k in z. So they're all on the real line, and they take this form. What I claim is that all of these complex numbers, these are isolated singularities, and what I claim is that they are all poles. So they are all poles actually of order 1. So one also says they are simple poles. Simple pole means pole of order 1. So let's check this, for instance, for the pole pi half. So pi half, I claim that is a simple pole. How do we check this? We can just write the Taylor expansion for cosine at pi half, and we obtain cosine of z is cosine of p half plus the derivative of cosine is minus sine, so minus sine of p half times z minus p half plus big O of z minus p half squared. And here cosine of p half is 0 and sine of p half is 1. So if we look at our function f, so we want to show that pi half is a simple pole. So we want to show that if we multiply our function by z minus p half, so we write z minus p half times f of z, we'll show that this function now has a removable singularity at p half. So if we do this multiplication, we obtain, so here we have z minus p half, here we have sine of z, and here the denominator, instead of cosine, we use its Taylor expansion to order 1, so we get minus z minus p half plus big O of z minus p half squared, and this equals, so we can simplify this with this and with this 2, and what we get is minus, is sine over z upstairs, and downstairs we have a minus 1 plus big O of z minus p half. And this function, when z converges to p half, the numerator converges to sine of p half, so to 1, and the denominator converges to minus 1, because here we have something which goes to 0. So this is converging to minus 1. So this converges for z going to p half, and therefore, by our first theorem, the singularity at p half of this function of the product is removable, and this shows that p half is a simple pole. Okay. So we have removable singularities, we have poles, and the third possibility is called an essential singularity. So the third possibility, the third and last possibility, so Z0, Z naught is called essential singularity. Z naught is, as usual, an isolated singularity of our holomorphic function f. It is called an essential singularity if it is not removable and not a whole. Okay, so the third possibility. So we'll see shortly with something about the nature of these singularities. Now let's see an example. Example 4. So we consider here the function f of z equals e to the power 1 over z. So the exponential function, but applied to 1 over z. So this function is holomorphic on c minus the origin. It's the composition of the exponential function, which is holomorphic everywhere, with the function mapping z to 1 over z, which is holomorphic here. And I claim that 0 is an essential singularity. So this means that if we multiply this function by z to the power k, so we have z to the power k times e1 exponential of 1 over z, no matter how large k is, even if k is very large, 0 will never be a removable singularity for this function. So this function has a singularity at 0 that is not removable for any natural number k. How do we check this? So the behavior of this function e to the power 1 over z for z going to 0 is rather complicated, but we can just restrict the attention to real and positive values of z. In other words, we look at the limit, so x is going to 0 from above, so this notation means in particular that x is a real number, so x here is real, and it's converging to 0 from the right. And we look at the function x to the power k exponential of 1 over x. What is the value of this limit? So here you can change variable, and you can call 1 over x, you can call it y. And so this becomes a limit of, so if 1 over x is y, now x was going to 0 from the right, so y is going to plus infinity. It's real. And here we have e to the y, and this x to the k becomes a y to the k, but in the denominator. And as you know, the exponential function of the real numbers divided by, so it grows faster than any power of y. So this limit is plus infinity for every k. So in particular, this function is not bounded in a neighborhood of 0, and therefore this singularity is not removable. So this is an essential singularity for this function. Okay, so these are the 3 different kind of isolated singularities, and the next thing will be to interpret, to see how the Laurent series of these singularities, of the function f near these singularities look like. So let me recall, so in the first lecture we have seen Laurent series. So again, we have our function f, domain in U, values in C, it's holomorphic. And now Z0 is an isolated singularity, which means that it's not in U, but there exists a punctured disk of radius r centered at Z0, which is contained in U. So a punctured disk is in particular, this is the same as the annulus 0r centered at Z0. Okay? With the notation of the first lecture. So this is the annulus where the inner radius is just 1 and the outer radius is r. So this is exactly the punctured disk. So our function f is holomorphic on this annulus, and as such it has a unique Laurent series. So we can write f of z equals sum n goes from minus infinity to plus infinity an z minus z naught to the power n. And this sum, we can also split it as first we write the regular part of the Laurent series, so the sum for n non-negative, n goes from 0 to infinity, an z minus z naught to the power n. This is the regular part. Plus, and then we can write the principal part of the Laurent series. So by renaming indices, this is a sum for m going from 1 to infinity. Here we have a minus m divided by z minus z naught to the power n. So here we have the negative powers of z minus z naught. And this is the principal part. Okay. So, general fact, our function is holomorphic on this punctured disk, and therefore on this punctured disk it has a Laurent series expansion, regular part, the holomorphic part. This would be actually holomorphic on the whole disk, and then instead we have the principal part. So, and our aim will be to read the nature of the singularity, of the isolated singularity Z0, in terms of the coefficients of our Laurent series. So let's start with the case of the isolated singularity. What I claim is that, of a removable singularity. What I claim is that Z0 is removable if and only if the principal part vanishes. There is no principal part, meaning that an is 0 for all n negative. So, one implication is clear. If the principal part is 0, if there is not this part, then f is just the sum of a converging power series, and we know that the converging power series will define a function which is holomorphic also at the center of the power series, so also at Z0. Okay, so this implication is clear. Let's check the other implication. So let's check that if the singularity is removable, then necessarily the principal part has to be 0. All these coefficients have to be 0. In order to do this, we can we choose a negative number, n. So it's an integer, so it will actually be n will be less or equal than -1, and we can write down the expression for the coefficient an. What we know is that an is 1 over 2 pi integral of the function f of z divided by z minus z naught to the power n plus 1 dz, and this is an integral on a circle surrounding z naught and contained in this punctured disk. So this is an integral on a circle k z naught whole, where rho is, write it here, is positive and smaller than r. Okay, this is the formula for the coefficients of the Laurent series, and in this case, so this number n plus 1 is less or equal than 0. So this we can also rewrite, let's rewrite it like this. This is 1 over 2 pi integral of f of z times z minus z naught, but now to the power minus n plus 1 in dz, again on the same circle. So what do we see here? This is the integral on this circle of a function which is actually holomorphic inside the disk, inside the whole disk dr z0. Well, f is holomorphic also at z0 because we are assuming that the singularity of f is removable, so we can give a value also at z0 in such a way that f is a holomorphic function. And here, the exponent here, minus n plus 1, this exponent is non-negative because n is less or equal than minus 1. So z minus z0, this is just a polynomial. It's also a holomorphic function. So we are integrating a holomorphic function on a curve which is bounding a region which is contained in the domain of this holomorphic function, and we know that in this case the integral is 0. This holds for all n less or equal than minus 1, so all the coefficients here appearing in the principal part have to vanish. Okay, so removable singularities are exactly those for which the principal part in the Laurent series expansion is 0. What about poles? Z naught is a pole if and only if the principal part in the Laurent series expansion is finite. Principal part is a finite sum. So in general, the principal part is a series, it's an infinite sum. But Z naught is a pole if and only if the principal part is finite. And more precisely, we can say that Z naught is a pole of order k, at least one, if and only if the principal part in the Laurent series expansion has the form a minus k divided by z minus z naught to the power k plus dots plus a minus 1 divided by z minus z naught with a minus k non-zero. Okay? Z0, Z0 is a pole of order k if and only if the principal part is this finite sum. You have some terms with lower powers of 1 over z minus z0. This could also be 0, but here the term with the power minus k is non-zero. So in other words, we can also rephrase it by saying z0 is a pole of order k if and only if a minus k is non-zero and a n is 0 for all n strictly less than minus k. So this is the characterization of poles in terms of the Laurent series. And the proof is you just apply what we proved in 1, so in the characterization of removable singularities, you just apply that argument but to the function z minus z naught to the power k f of z. Okay? And you will obtain immediately this statement. Okay, these are poles, and now the last possibility is the possibility of an essential singularity. And of course, now Z0 is an essential singularity, is essential if and only if. So we're in the case not covered by 1 and 2, meaning that an is different from 0 for infinitely many n negative. Or in other words, the principal part of the Laurent series is a true series. It's not 0 and it contains infinitely many terms which are non-zero. Okay? Just because this is now the only case which is remaining. Okay. So maybe it's time. And yeah, we can also look back at the example. What was that? Example 4. In example 4, we were looking at the function f of z equal e to the 1 over z. And what is the Laurent series expansion of this? This is easy to find. We just use the power series expansion of the exponential, and we get the sum n from 0 to infinity, 1 divided by n factorial, 1 over z to the power n. So here, in the Laurent series expansion of f, we see this is 1 plus sum n goes from 1 to infinity, 1 over n factorial, 1 over z to the n. So this is the principal part, this is the regular part, 1. This is just a constant function, the regular part. And the principal part, this one here, is now an infinite series. In this case, all its coefficients are non-zero. So again, we see that 0 is an essential singularity for the function e to the power 1 over z. Very good. Now I would like to tell you just a little bit more about how you create functions with poles and something about essential singularities. But first we deal with poles. So recall something about zeros of a holomorphic function. No? If f is a holomorphic function and U, holomorphic, U is an open set, and Z0 is now an element of U, such that f of z naught is 0, so it's a 0 of this function. Then you have seen in the first part of this course that there are two possibilities. Either f is identically 0 on the whole connected component of u containing z naught, on connected component of u containing z naught, or z naught is an isolated 0. Z naught is an isolated 0. Meaning that there exists a punctured disk centered at z naught in which there are no zeros. Okay, this you have seen in the first part of the course. And then, so let's say that we are in this situation. Z naught is an isolated 0. In this case, it makes sense to consider the function 1 over f. 1 over f now will have a singularity at z naught. And what I claim is that 1 over f has actually a pole at z naught. This is the claim. So when I have a function which at z naught has an isolated 0, then the inverse of this function, the reciprocal, so with respect to multiplication, 1 over f, has a pole at this point. So how does one prove this? We can use again the power series expansion of f. So f is a holomorphic function, so it has a power series expansion of the form f of z is the sum n goes from 0 to infinity, a n z minus z naught to the power n. And this on some disk centered at z naught. But z naught is a 0 of this function. So we obtain that a naught, the first coefficient, is 0. Then let k be the smallest natural number such that ak is non-zero. So some of these coefficients have to be non-zero, because otherwise, if they're all 0, then the function f will be identically 0 in a neighborhood of z naught, therefore the connected component containing z naught. So we know that this is a non-trivial power series, so there is a first k such that ak is different from 0. And then this means that f of z is ak times z minus z naught to the power k, and what remains is a big O of z minus z naught to the power k plus 1. This is f. Now let's look at, you raise up here. I will erase here and write here. The top part of the blackboard. So we wanted to show that 1 over f has a pole at z naught. And actually we show that if we multiply 1 over f by z minus z naught to the power k, so z minus z naught to the power k times 1 over f of z, we show that this function now has a removable singularity at z naught. So what is this? We use this expansion and we obtain 1 over, so if we plug for f of z, we plug this expression, we can then divide by z minus z naught the k, and we obtain, here we have a k plus big O of z minus z naught. And this function, when z converges to z naught, converges to 1 over ak. Remember that ak is non-zero for z going to z naught. So this fact shows that z naught is a removable singularity for this product, and therefore z naught is a pole of order at most k of f. Okay? And actually you can also check that under this assumption the order of this pole is precisely k, because you can check that if you here you multiply by a smaller power of z minus z naught, the result will be a function which actually diverges. So in absolute value it goes to plus infinity when z converges to z naught. Okay, so this shows that if we take a function with an isolated zero and then we look at the inverse of this function, 1 over f, we obtain a function which has a pole. Okay? And you can also, I leave it as an exercise to try to understand how the order of the pole is related to the number of derivatives of the function, of the original function f, vanishing at z naught. Okay. I also leave you as an exercise to check the fact that if z naught is a pole, then the limit for z going to z naught of the function f of z in absolute value is plus infinity. So, near a pole, the absolute value of a holomorphic function diverges. Near a removable singularity, instead, the holomorphic function is converging to some finite value. And what happens near an essential singularity? The answer is given, or say, a partial answer is given by the following theorem, which will be the last theorem of this lecture, and which describes something about the behavior of a holomorphic function near an essential singularity. And this theorem is named after Casorati and Weierstrass. So it's the Casorati-Weierstrass theorem. It says the following. So, Z naught is, by assumption, an essential isolated singularity. Of f. F is as usual our holomorphic function from U to C. Then we consider an arbitrarily small punctured disk centered at Z naught contained in U. So for any R positive such that this puncture disk D prime R C naught is contained in U, we look at the image of this puncture disk through the map F. We look at the set F of D prime R C naught. Okay, so we look at the values that F attains near Z naught. So we know actually that this is some open subset of C, because holomorphic functions or non-constant holomorphic functions are open maps. They map open sets into open sets. So this will be an open subset of C. And what this theorem says is that this set F of the puncture disk is actually dense. In C. Okay. So this means that near Z naught, F achieves really many values. It achieves, the set of values which are achieved by F is dense in C. So whenever I fix a complex number, I can approximate this complex number arbitrarily well by F of some number contained in this disk, this puncture disk, no matter how small this puncture disk is. Okay? So this shows that F has a very complicated behavior near Z naught, because a whole, let me make a picture. So this is our singularity Z naught. We take a very small puncture disk centered here, and the image of this disk is really invading the whole complex plane. It's defining some open set which is dense in the whole complex plane. So this is mapped really everywhere. Okay, everything is, and this no matter how small this radius R is. Okay, let's prove the Casolati-Weierstrass theorem. So the proof will be a proof by contradiction. So assume not. Assume not means we are now assuming that the image of this disk, so there exists, assuming that there exists some R positive with this puncture disk contained in EU, but the image of this puncture disk is not dense. What does it mean that it's not dense? It means that there exists some complex number, let's call it W, and there exists a positive real number, let's call it epsilon, such that, so the image of this remains epsilon far from W, or, so F of Z minus W in absolute value is greater or equal than epsilon for all Z in this puncture disk. Okay? So here we are exactly saying that the image is not dense. The closure of the image does not contain the point W. Okay. In this case, we can define a new function g. G of Z, we will define it as 1 over f of Z minus W. So, by this assumption, in particular, in this puncture disk, the difference f of Z minus W is never 0. So, this function g is well defined on d prime R Z naught. So it's well defined here. And moreover, the absolute value of G, this is the inverse of this absolute value, so it's less or equal than 1 over epsilon, since this absolute value was greater or equal than epsilon for every z in this punctured disk. So we have G. G is of course a holomorphic function. F was a holomorphic. We are removing a constant and then we are taking the inverse. So G is a holomorphic function on this punctured disk and it's bounded. So the first theorem we proved today, this theorem on removal of singularities, tells us that G has a holomorphic extension. So the singularity at Z0 for G is removable. So G has holomorphic extension at Z0. Okay? So G of Z0 is then well defined. We can define G of Z0 as the limit of G of Z for Z going to Z0, and we will obtain a function G which is now holomorphic also on this disk. And now we look again at F. So from this expression we get that f of z is, so f of z minus w is 1 over g, meaning that f of z is 1 over g of z plus w. And now we look at this expression. So now we have two possibilities. Either g, so we said G is now holomorphic on the whole disk. Now G is holomorphic on dr Z0. Okay, we have removed the singularity. So either G at Z0 is non-zero. Well, if this is non-zero, 1 over G is actually a nice holomorphic function near Z0. And therefore, this f, now it's 1 over g, but this is holomorphic, this is a constant, then f will be holomorphic everywhere. In particular, it will be complex differentiable at Z0. But, so this would mean that Z0 is a removable singularity for f. But instead, we were assuming that Z0 is an essential singularity of f. So this cannot be. The other possibility instead is that g of Z0 is 0. This, of course, is possible, but notice that g is not identically 0, because for z different from Z0 is for sure not 0. And therefore, Z0 in this case would be an isolated 0 of the function g, and we just proved that in this case 1 over g would have a pole at Z0. So we are given a constant, then we would get that f has a pole at Z0. So Z0 would be a pole of f. And this is also a contradiction, because we were assuming that the singularity Z0 is essential. So the conclusion is that our assumption by contradiction was wrong, and so the image of this punctured disk is actually dense in Z. Okay? So this concludes the proof of the Casorati-Weierstrass theorem. And so this is one way of stating this theorem. Let me finish by mentioning an immediate corollary of this theorem. So, corollary. let's now consider an entire function. So entire means it's a holomorphic function on the whole complex plane. But let's assume that it's entire, but not a polynomial. Polynomials are entire functions, but we're assuming that we have an entire function which is not a polynomial. For instance, f could be the exponential function, could be sine, cosine, one of these functions. Then, for all r positive, the image of the complement of the disk of radius r, so C minus disk of radius r centered, for instance, at 0, this image is dense in C. Okay? So this is a corollary of the Casorati-Weierstrass theorem. To prove this, you just have to apply the Casorati-Weierstrass theorem to the function f of 1 over z. Okay? If you consider this function will have a singularity at 0. And so this function, first of all, is well defined, has an isolated singularity at 0, so it's well defined in a punctured disk centered at 0 because f was defined on the whole complex plane. The fact that f is not a polynomial will tell you that this function has a singularity at 0, which is essential. And then by applying, then you can apply the Casorati-Weierstrass theorem, and you will get this result. Okay, let me conclude this lecture just by mentioning that so this theorem, the Casorati-Weierstrass theorem, and its corollary, these are actually not the end of the story. One could actually say more about this set. This set is not only dense, one could actually prove that this set is either the whole C or it's C minus 1 point. Okay, so it's really a huge set. You can leave out at most 1 point. And this result is known as the Picard theorem, the big theorem of Picard, but this is a theorem whose proof is considerably more complicated than the proof of the Casorati-Weierstrass theorem we saw today. So that's it for today, and see you next time.